Hello everybody, welcome to the second part of Gravity Dam. This video includes stability analysis and modes of failure, different types of loading and load combinations, safety of gravity dam against overturning, forward sliding and overstressing. This video also includes elementary and practical profile of gravity dam, limiting height of gravity dam, various components of gravity dam, grouting in dam and finally instrumentation in dam. This presentation is prepared by Anis K. Assistant Professor, Department of Civil Engineering, MEA, Engineering, College, Perinthalmanna. The stability analysis of a dam section is carried out to check the safety against rotation and overturning, translation and sliding, overstress and material failure. Overstressing and material failure can occur by two ways, by compression or crushing, or by the development of tension in dam body. For the considerations of stability of a concrete gravity dam, the following assumptions are made. The dam is composed of individual transverse vertical elements, each of which carries its load to the foundation separately. Stability analysis is carried out for the whole block. Vertical stress varies linearly from upstream face to downstream face on any horizontal section. The different types of loading can be classified into different categories. Forces that give stability to dam are weight of dam, thrust of tailwater. Forces that destabilize the dams are static forces and dynamic forces. Destabilizing static forces are reservoir water pressure, uplift pressure, ice pressure, temperature stresses, silt pressure. Destabilizing dynamic forces are seismic forces, hydrodynamic pressure, forces due to waves in the reservoir, wind pressure. The design of gravity dam should be done for two cases: when reservoir is full, and when reservoir is empty. Load combinations taken for design are mainly two categories as normal load combination and extreme load combination. Normal load combinations are water pressure up to normal pool level, normal uplift, silt pressure, and ice pressure. This load combination is taken when ice force is more. Water pressure up to normal pool level, normal uplift, earthquake forces and silt pressure. Water pressure up to maximum reservoir level, normal uplift, and silt pressure. Extreme load combinations is water pressure due to maximum pool level, extreme uplift pressure without any reduction due to drainage and silt pressure. The dam is considered safe against overturning at any horizontal plane if no tension in the upstream face is allowed. A factor of safety against overturning not less than 1.5 is attained. Equation to find out the factor of safety against overturning is given here. The diagram shows development of overturning moment and resisting moment. Before a gravity dam can physically overturn, cracking of upstream material due to tension, increase in uplift, crushing of the toe material and sliding may occur. Many of the loads of the dam act horizontally like water pressure and earthquake pressure. These forces have to be resisted by shearing forces at any horizontal or nearly horizontal planes and foundation. The dam is considered safe against forward sliding at any horizontal plane if a factor of safety is attained as given by the equation. A general formula is also given to calculate the factor of safety against forward sliding. These diagrams show the interface between dam base and rock, to show the development of shear force. A dam may fail if any of its part is overstressed, and hence the stresses at any part of the dam should not exceed the allowable working stress of concrete. Hence the strength in dam concrete should be more than the anticipated in the structure by a safe margin. The maximum compressive stresses occur at heel when reservoir empty condition, or at toe when reservoir full condition, and on planes normal to the face of the dam. For design considerations, the calculation of the stresses in the body of the dam follows from the basics of elastic theory, which is applied in two-dimensional vertical plane. And assuming the block of the dam to be a cantilever in the vertical plane attached to the foundation. The contact stress between the foundation and the dam, or the internal stress in the dam body, must be compressive. Development of tensile stresses in the dam body will lead to the failure of dam in tension. Next we have to discuss about the elementary profile of gravity dam. When water is stored against any vertical face, then it exerts pressure perpendicular to the face, which is 0 at top and maximum at bottom. The required top thickness is thus 0, and bottom thickness is maximum, forming a right-angled triangle with the apex at the top. One face vertical and some base width. Two conditions should be satisfied to achieve stability. When empty, the external force is 0 and its self-weight passes through the center of gravity of the triangle. When full, the resultant force should pass through the extreme right end of the middle third. Various forces we considered to be acting in the elementary profile are given here. Figure shows the elementary profile of gravity dam with forces and their point of actions. Water pressure P acting at point D, weight of dam W and uplift force U passing through point M1 in opposite directions, and resultant force R passes through point M2. Now we are moving to the practical profile of gravity dams. Elementary profile of gravity dam is only a theoretical profile which is not possible in practice because of the provision of roadway at the top, additional load due to roadway, freeboard. Due to these provisions, the resultant force of the weight of the dam and the water pressure falls outside the middle third of the base of the dam when the reservoir is full. To eliminate tension, some masonry is provided in the upstream side of dam. Top width of the dam is fixed according to requirements of the roadway to be provided. The most economical top width of the dam is 14% of its height. Base width of the dam shall be fixed in such a way that the dam should be safe against overturning, sliding, and no tension is developed in dam body. Freeboard is the margin provided between top of the dam and high flood level in the reservoir, to prevent the splashing of water. It also take care of any unforeseen floods in the reservoir. According to IS 6512-1972, the freeboard is usually provided as 1.5 times the wave height corresponding to above full reservoir level condition, or for the maximum water level condition, whichever is higher. In any cases the freeboard shall not be less than 0.9 m above the maximum water level. Wind velocities of 120 km per hour, over water in the case of full reservoir condition, and 80 km per hour, over water in case of maximum reservoir condition are generally assumed for calculation of wave heights. According to revised code recommendations in IS 6512-1984, the freeboard calculation is given here. Wind velocity is taken as 120 km per hour for normal reservoir level condition and 80 km per hour for maximum reservoir condition in the case of revised code recommendations. The freeboard shall not be less than 1 m above the maximum water level in any cases. Modern practice is to provide a maximum freeboard of 3% to 4% of the height. Though freeboard equal to 5% or more might prove economical. Diagram shown here is the practical profile of a gravity dam. Now we shall move to the topic, limiting height of low gravity dams. A low dam has limiting height such that the resultant of all forces passes through the middle third of the base, and the maximum compressive stress at the toe does not exceed the permissible limit given by this equation. For a low gravity dam, the height of dam should not exceed the height calculated with the above equation for limiting height. A low dam will be having the shape as elementary profile of gravity dam. Coming to the limiting height of high gravity dams, the dam for which the height exceeds the limiting height of low dam is termed as high dam. In this case, the resultant of water pressure and self-weight of the dam passes out of the middle third of the base. It may lead to the development of tension in dam body. Hence the dam profile to be adjusted by adding extra slope on the upstream and downstream sides to limit the compressive stress within the permissible limit. Next we are discussing about different components of gravity dams. First of all we are discussing about shafts. Shaft is a vertical opening provided in the dam. Shafts connect galleries at various levels. Shafts are generally provided with lifts, so as to conduct effective inspection of the dam, and also to facilitate quick approach anywhere in the dam. They are sometimes used to measure the deflections of the dam also. Then we have to discuss about keys. It is a device, with the help of which shearing stresses from one block are transferred to the adjacent block. The provision of keys is essential for longitudinal joints but optional for transverse joints. The adjoining surfaces of each block are given such a shape that they, together with transfer of stresses, cause effective interlocking also. Keyways may be of several shapes such as triangular, trapezoidal, or trough-shaped. Water stops. The main job of water stops is to prevent leakage from the dam. They may be made of copper, steel, sheet, lead, or of natural rubbers and plastics. Metal water stops are provided only in the case of non-yielding foundations. Rubber water stops are used in case the foundation is of yielding type. Drainage wells filled with asphalt are also sometimes used, along with water bars. Water bars are also a type of water stops. Another important component is gallery. Galleries have to be left in the gravity dams during their construction. The size of the galleries depends upon the purpose they have to perform. The galleries may be aligned both along the axis and across the axis of the dam. They are provided at all the levels of the dam. All the galleries are given some longitudinal slope and small channels along both the edges of the galleries are formed. Seeping water through the dam section is collected by the channels running along the galleries. Since channels have longitudinal slope, the collected water in channels keeps on flowing automatically, and is collected at some central place from where it is discharged into the downstream side of the dam. There are three major types of galleries in any dam structure. Service galleries are used for piping for fluids such as water, hydraulic oil, and compressed air to operate lock and spillway gates, as well as conduits for electrical wiring, networking cables, telephone and communication lines. Pump galleries are located in the foundations of dams, and contain submersible pumps to dewater the dam, or remove what water seeps into the dam structure. Observation galleries are used to extract soil samples from under the dam foundations as well as to check on the integrity of structural components, such as rebar used in the construction. Most generally galleries fall into different combinations of these, and are also used as simple pedestrian tunnels for the gate operators. These galleries also will contain things such as fire alarms, fire sprinkler systems, and electrical lighting. Shape of the gallery is generally rectangular, but it may be oval-shaped also. Side channels are provided on both the sides of the gallery. Now we are going to discuss about the functions of galleries in gravity dams. The functions are: the seeping water would create internal stresses in the dam and may cause its failure. Galleries intercept the seeping water and relieve the dam from internal stresses. They form a path to reach each and every part of the dam. They are used for dissipation of heat, developed by setting action of the cement concrete during construction of the dam. They are used for plugging the longitudinal joints of the dam, after the dam has been completed. They are used to carry out drilling and grouting of the dam or the foundations. They are used to study the behavior of the dam after completion. They are used for fitting mechanical equipment like pumps etc. in them. Galleries are also essential for operation of sluice gates, outlet gates etc. Now we are going to another topic related to gravity dams. That is grouting. Dam grouting is a proven methodology for installing barriers in dam foundations against the seepage of water. In this application, these barriers are often called grout curtains. This technique is employed where the rock formation beneath the existing or proposed dam foundation is so pervious that seepage problems are expected. Grouting can extend the life of existing structures that have experienced severe degradation due to seepage, scour or freeze, thaw damage. Grout curtains will block the movement of seeping water through the dam bottom. An example is given below to explain how a dam is protected from the damages caused by seeping water with the help of sketches. Next we are going to see how grouting protects our gravity dams from damage. It is explained in 4 steps with the help of neat sketches. Step 1. the stored water exerts a horizontal pressure against the upstream face of the dam. Step 2, the weight of the dam, acting downwards, counteracts against the water pressure to stop the dam overturning about the downstream toe. Step 3, if there is no grouting under the dam, seepage can potentially pass along open cracks at its base and exert pressure upwards. This acts to reduce the effect of the dam's weight and therefore reduces its safety. The illustration shows a dam tilting about its downstream toe, because the dam has insufficient weight. To withstand the combined effect of storage pressure and uplift pressure, step 4, when a grout curtain intercepts the seepage, and thereby cuts off most of the uplift pressure, the dam's stability is improved. The final topic we are going to deal with is about the instrumentation in dams. Instrumentation is the process of installing various instruments in the dam to monitor the performance of the dam, during construction, during initial reservoir filling, and during the life of the structure. Any instrument installed should target the evaluation of a specific parameter. Instrument will give data by analyzing the dam for particular parameters specified to it. From the data collected by instruments, the required action is suggested and executed. Let us check why instrumentation is necessary in a dam. It is done for executing the following functions: to collect basic parameters like forces and material properties in quantitative form to help designs, to keep constant watch over performance of the structure during service and obtain a timely warning, to assess the real significance of various parameters used in designs, and thereby modify designs procedures and criteria leading to increased economy and safety, to evaluate the permeability of casing soils, and their performance in sudden drawdown condition. On the upstream side needs to watch, to measure the pore pressures within the body of the dam. If the dam is located in a seismic zone, then the vertical settlement as well as horizontal settlement of the dam to be measured. Spread on the upstream and downstream needs to be monitored, particularly in its early life. The behavior of dam for comparison with the design assumptions is to be observed. If the dam lies in heavy rainfall zone, both in intensity and quantum, then it would be required to find out how far does the heavy rainfall affect the saturation of downstream slope, even after provision of pitching, backed by quarry spalls on the downstream slope. With the advent of finite element analysis method, it is possible to predict stresses, settlements and pore pressures to a greater degree of accuracy. Comparison of the results of such analysis with observations on prototype will be possible by providing the instrumentation. In short, the instrumentation in dam will give an excellent opportunity for checking design assumptions made and parameters assumed in the stability analysis. In this portion, we can see different instruments, which can be installed in a dam, and the functions to be performed by those instruments in analyzing the performance of the dam. It is provided in tabular format, as instrument in one column, and the corresponding parameter me's read by the instrument in the next column. Thank you for watching the video.